Let's look at the impulse momentum equation graphically. We have impulse is F delta t, force times the time that it's exerted over. Force is inversely proportional to delta t. So, for example, if we change delta t by just a little amount, we can greatly change the force exerted on an object. For example, let's take this point over here. The time there is a little less than 1 second, and the force is about 130 newtons. If we just change to about 4 seconds, if we extend the duration of the impulse to 4 seconds, you can see how the force drops dramatically. And as you go longer and longer at your time interval, there's less of a change in force because frankly it's getting very tiny. Another way to look at that is we have impulse divided by delta t equals the force applied. So you can see as delta t gets smaller, F gets a lot bigger. Now we're just going to work with the magnitudes of the impulse and momentum going forward, so we're going to leave the vector sign out for now. The bold here is to show that if delta t is small, F is large. If delta t is large, F is small. The inverse relationship of force and time interval leads to many interesting everyday applications of the impulse momentum equation, such as car structural safety design, car airbags, landing on the ground after you parachute safely from an airplane, the martial arts, and both hitting and catching a baseball. We're going to look at two specific cases from the previous list: car airbags and hitting a baseball. The analysis we're going to use is very helpful. You can use it in many other cases in physics when you have an equation with 3 variables. In this case, the 3 variables are force, your time interval, and of course, impulse, which again is your change in momentum. So you have the 3 variables. You have to decide, depending on what case you're analyzing, which value is fixed and then which will be varied, and then that will determine the impact on the 3rd variable. For example, for the car airbags, we'll fix delta p, we'll take different scenarios of the time interval and see what the impact on the force is, and in this case it'll be the force on the people inside the vehicle. For a bat hitting a ball, we will fix the force with which the player hits the ball, we'll vary the time interval, that's how long the ball stays in contact with the bat, and we'll see what that does to the momentum of the ball. In the dynamics unit of this course, it was shown how during an accident, seat belts protect passengers from the effect of Newton's first law, the law of inertia, by stopping the passenger with the car and preventing them from striking the dashboard and the window. Inertia, the law of inertia, says you keep moving until there's a force that stops you. That's one of the things it says. So if you are not seat belted in, the car stops because it hits something or you apply the brakes very quickly. And if you are not seat belted in, the frictional force between your body and the seat is not enough to stop you. So you'll go flying forward as the car stops, which is never a good idea. Also, the seat belts provide another benefit explained by the impulse momentum equation, and this benefit is greatly enhanced by the presence of airbags. Can you see what this benefit is? Take a second before you go on to the next slide and see if you can figure it out. The time interval delta t. The seat belt increases the time interval that it takes the passenger to slow down. You don't go flying forward and hit the glass. The seatbelt has a little play, so you move a little bit, but then it slows you down when it tightens up. The biggest effect here is the airbag. That increases that time interval. It rapidly expands, providing a cushion that you strike. Then it deflates, and it's slowly compared to how fast the car has stopped, bringing you to a stop. Very analogous to if you fall from a height of 3 feet onto the floor, that hurts. Your time interval of this stop is very, very short. If you fell the same height onto a mattress, the mattress would give, increasing the time of you stopping. There'd be a greater time interval. Earlier we stated that delta P for this example, for the car airbag would be fixed and delta T would be varied. Well, we just talked about why delta T is varied. Why is delta P fixed? Delta P is fixed because as long as the passenger remains in the car, which of course is another wonderful reason to wear your seatbelt, the car and the passengers started with a certain velocity and finished with a final velocity of 0 independent of the seats or the airbags. Whether you had them on or not, the car is going to stop. By rearranging the equation, F is delta P over delta T, where F represents the force delivered to the passenger due to the accident. We have the impulse momentum equation up here, where F delta T is equal to the change in momentum. And we did a little rearranging on the last page, and we had force is delta P over delta T. So delta P is fixed. So we just draw a little horizontal line there showing that it's fixed. Delta T, we've extended the time interval by using the seatbelt and the airbag. So delta T is going to increase. This is a handy little trick to see what happens to the various variables. If you increase the denominator, you decrease the entire number. So the force, and this is the force on the passenger, decreases markedly. That will mean less physical harm to the people inside the car. Another benefit from the airbag is pressure. Pressure is force per unit area. By increasing the area of the body that feels the force, remember the airbag is pretty big, less pressure is delivered to all parts of the body. That will reduce the chance of puncturing the body, which is also a very good thing.